everyone. Welcome back to another DSA tutorial. Today, we're diving into one of the most important data structures in computer science, the red-black tree. If you want the best animated tutorials about data structures and algorithms, make sure to visit our website, AlgoPK.com. We've got tons of interactive visualizations just like this one. All right, let's get started. So what exactly is a red-black tree? Simply put, it's a self-balancing binary search tree where every node has an extra attribute, a color. And that color can be either red or black. Now, you might be thinking, why do we need colors in a tree? Great question. The colors help us keep the tree balanced. You see, in a regular BST, if we insert elements in sorted order, we get a skewed tree, basically a linked list, and that ruins our log n performance. Red-black trees solve this problem by using colors and some clever rules to keep the tree approximately balanced. This guarantees log n time for search, insert, and delete operations. Now, here's the key part. Every red-black tree must follow these 5 properties. Watch the animation carefully. Property 1. Every node is either red or black. Simple enough. Property 2. The root is always black. Remember this one. It's important for the fix-up operations. Property 3. Every leaf node, we call them nil or null nodes, is black. Property 4. This is crucial. If a node is red, both its children must be black. In other words, no 2 red nodes can appear consecutively on any path. Property 5. Every path from any node to its descendant nil nodes must have the same number of black nodes. We call this the black height. These 5 properties guarantee that the longest path is at most twice as long as the shortest path. That's how we maintain balance. Now, let's talk about rotations. When we insert or delete nodes, we might violate these properties. That's when rotations come in. There are 2 types. Left rotation. Watch the animation. When we left rotate on node X, its right child, Y, moves up. X becomes Y's left child, and Y's left subtree becomes X's right subtree. Right rotation is the mirror operation. Node Y's left child, X, moves up. Y becomes X's right child, and X's right subtree becomes Y's left subtree. These rotations take constant time, O of 1, and they preserve the BST property. Pretty elegant, right? Now, let's see how insertion works. Step 1. Insert the node just like a regular BST insertion. Step 2. Color the new node red. Why red? Because inserting a red node doesn't change the black height of any path. Step 3. Fix any violations. Now the fix-up has 3 cases. Watch the animation. Case 1. The uncle is red. We recolor the parent, uncle, and grandparent. Then we move the problem up the tree. Case 2. The uncle is black, and we have a triangle shape, like left-right or right-left. We rotate the parent to convert it to case 3. Case 3. The uncle is black, and we have a line shape, like left-left or right-right. We rotate the grandparent and recolor. Done. After all this, we make sure the root is black. Deletion is a bit more complex. If we delete a black node, we might violate property 5, the equal black heights rule. We handle this with something called double black. When we delete a black node, we create a double black situation that we need to fix. There are 4 cases for deletion fix-up. Case 1, sibling is red. Rotate and recolor to convert to other cases. Case 2, sibling is black with 2 black children. Recolor and move up. Case 3, sibling is black with far nephew black. Rotate sibling to get to case 4. Case 4, sibling is black with far nephew red. Rotate parent, recolor, and we're done. The good news is, at most 3 rotations for delete, and at most 2 rotations for insert. Now, quick comparison with AVL trees. AVL trees are strictly balanced. The height difference between subtrees is at most 1. That means faster searches. But red-black trees are more relaxed. They do fewer rotations during insert and delete operations. So if your application has lots of insertions and deletions, go with red-black. If it's mostly lookups, AVL might be better. That's why red-black trees are used in Java's tree map, C++'s map and set, and even the Linux kernel's scheduler. Now let's look at the code. I'll walk you through the key parts. In C, we define a node structure with data, color, left and right pointers. The nil is a sentinel node that's always black. The left rotate function takes node X and its right child Y. We reassign pointers to move Y up and X down to the left. The insert fixup function handles the 3 cases we discussed. We loop while the parent is red, check which case applies, and do the appropriate rotations and recoloring. In C++, we use a template class for flexibility. The node is an inner struct. The logic is the same, just with cleaner C++ syntax. In Java, we use Boolean for colors, true for red and false for black. The compare-to method handles the comparison, same rotation and fix-up logic. In Python, we create color and node classes. The code is very readable. The insert fixup method handles all 3 cases with clear if-else statements. The key takeaway from all implementations: insert as red, then fix violations by checking uncle's color and performing rotations as needed. Always end by making the root black. And that's red-black trees. To summarize, self-balancing BST using red and black colors, 5 properties that maintain balance, left and right rotations to fix violations, O of log n guaranteed for all operations, and fewer rotations than AVL for modifications. Practice inserting and deleting nodes using the interactive visualization. Understanding the cases takes time, but once it clicks, you've got it. For more amazing animated tutorials on data structures and algorithms, visit our website, AlgoPK.com. We've got everything from arrays to graphs, all with beautiful visualizations like this one. Thanks for watching.